In the previous video, we talked about how we can modify a typical OpenFOAM case and code, particularly which shows the icoFoam solver, and we inserted the temperature field in it. In this video, let's add buoyancy to that solver. For this, we'll use the Buossinesq Approximation. So let's begin. Let us take a typical 2D case with an obstacle inside. In the previous video, we had taken a case like this where we had heated the internal obstacle to a relatively higher temperature. This time, we'll model the natural convection heat transfer between the annulus, and we'll use the Buossinesq approximation. If we look at the governing equations, again I assume a 2D case, an incompressible case, we'll write the continuity equation, then we have the momentum equation, and we have the energy equation. Now here, for the Buossinesq approximation, we'll add a source term g beta delta t in the momentum equation, and this is how the energy and the momentum equation will talk to each other. The temperature from the momentum equation will come from the energy equation, and the velocity from the energy equation will come from the momentum equation. For natural convection, the governing non-dimensional number is Rayleigh number, and this is how we calculate it. Now let us look one by one what are the changes that we should make to the code in order to implement this. The first thing is that we need to include a source term in the momentum equation. So we'll have to also define all the terms that are included in these source terms. So we'll define this in the createFields file. Once we do this, we will also change the way we were defining the thermal diffusivity. We will define it as nu by PR instead of alpha, so that we can incorporate the Rayleigh number part better. And in the main code, we will implement this source term, and we'll see what are the changes that we need to make. So in the createFields file, the first thing that we do is we will add the constant parameters that are required for defining the Buossinesq approximation, g beta delta t. So we define all those things. We make sure that the dimensions are defined properly. We also need to define g, which is the gravity parameter, and it will be defined like this. And then we will have the joint source term, we'll call it as buoyancy term, and we'll implement it this way. Now, if we talk about the main code, so in the main code, we first need to add this term so that our source term gets updated as and when the temperature field is calculated, and we will add the source term, the buoyancy term, when we are including the momentum predictor, so that the corrected velocity is used based on the pressure correction. So this is the simple addition that needs to be done. Once that is done, we will simply go ahead and compile the code. And once the code is compiled, we can move to the case. And if we talk about the case, the temperature has to be updated because of the boundary condition, and so we'll also check the velocity and pressure. And then in the constant folder, the G and transport properties in the system, probably we may define or refine the mesh. Again, it's optional. It's all based on the accuracy that we want. So moving on to the pressure file, nothing to be changed. Moving on to the velocity, I'll make all the walls no slip. And if we talk about the temperature, will retain the same boundary conditions that were before. So this is done. Let us move to the constant folder. In constant folder, we will update the value of G. Now, how do we decide what value to use? We'll talk about it. And in transport properties, I'll define all the other constant values. Again, here we'll talk about this. Now, if we look at the Rayleigh number, we have G beta delta T L cube upon alpha square, ergo nu square by PR square. PR square goes to the numerator, nu square to the denominator. Say we use a Rayleigh number of 10 raised to 5. I assume the beta to be 1, delta T to be 10, L cube based on the dimension B is 1, and Prandtl number I assume 1. The kinematic viscosity currently is 10 raised to minus 2, 10 raised to minus 4 it becomes, and therefore if we calculate everything we get the value of G as 1, and which I substitute. In system, again block mesh, it's up to you. If you want to refine it, it will be better to capture the thermal boundary layer. Don't go crazy at the initial stage. We'll keep it a little coarse so that we can run the case faster and debug. And once you run this, you should see something like this. All right. Now, let us try to then run the command. And if you try to post process, you should see some contours like this. Obviously, the thermal plume will rise upward because of the buoyant forces in action. And if you pull out the contours, you should see something like this. So very beautiful. This is the end of this tutorial. Thank you.